Yeah.
Yeah.
Okay, so we're gonna keep on doing stuff with polarization. What happens on Thursday?
We have, I think, I don't know.
My people, we have an exam. Well, my people are invited. Again, the first three people get free beer, pizza, and pony cards.
Really?
The first three people just like, oh, like that's
All of it? Whoa. I didn't get any free beers.
for the first three people.
I was
You're in the first three.
clearly not.
Did you get beer? No,
No.
because you were on the first three. Yeah.
If we get the beer, are we allowed to resell it?
You're not. You're not. Okay, so let's go over what we did before. So we said that when we have a non-homogeneous differential equation, so for non-homogeneous linear differential equations, where the f of x term is simple. What do we mean by simple?
Exponential.
Exponential.
Sine, cosine.
Sine and cosine.
Polynomial.
Polynomial.
Exponential.
Constants.
No.
And then products of those. Okay. What do? Take f of x, and what do we keep on doing?
Take the derivative.
We keep on taking derivatives.
Then we find
First derivative, second derivative. What do? We look for
a unique.
pieces. So, you know, maybe this is unique, maybe, well, maybe this is not. Maybe we have, let's see, maybe this is unique. We take, basically, we said the non-homogeneous piece here is a linear combination of unique pieces of f of x and its derivatives. Then what do? We need to determine the coefficients, and how do we do that?
But we take all the unique pieces multiplied by like the coefficient.
How do you determine the coefficients? You take it, and you put it back in the differential equation, and by putting it back in there, you can determine what those coefficients are. And this method is called the method of
Simplicity.
undetermined coefficients. Okay, that's what it's called. That makes sense? So why doesn't this work for the L? I mean, ln of x is an easy function. Why would this method fall apart badly for the ln of x? So why can't we use this method for f of x equals a log of x?
Because it's every time you derive it.
Yeah, what happens is you keep on taking derivatives, so stop. No, you keep on getting unique pieces, and it doesn't. So basically, there is no method to the unique derivatives of f of x. Okay, that makes sense. That's why we just have those terms that we do, and life is all good and well. And so, how did we go about doing this to our problem here? We have this problem here. And we applied a driving term to it like this. And we said that this is our x equals 0. This is k. This is m. So this goes out to here. Here's our wheel. That. If you take this driving term to be some f naught sine omega t or f naught cosine omega t. Ooh. You're so good. Okay. Or how else did we take it?
The exponential.
Is this e to the I omega t? Now, what is this omega referred to?
Angle of frequency.
Of what?
See if
That's the omega of this wheel going round and round. Okay. What is omega naught?
The natural frequency of oscillation of the spring.
Yeah, so omega naught is the natural frequency of oscillation of the spring. This is K over. Does that make sense? And so we set up this differential equation. What did we have? Oh, is this material on the exam?
No.
I lied. No, it is not on the exam. Okay, it's not on the exam. Where's the material stop?
Somewhere.
Okay.
The like
What have I guaranteed you is going to be the first question?
derive Maxwell's equation for linear isotropic dielectric.
Okay, so part A is going to be what, right?
Maxwell's equation.
Maxwell's equations in differential form, and give them names. What is part B of that going to be?
For what I just said.
Okay, you're gonna, but how are you gonna read? In terms of H, D, E, and B. Okay. That makes sense?
So write them or derive them.
Derive them.
Okay.
Okay. And what will I give you? $1. Now, what will I give you? I will give you JM,
Oh yeah.
which is
J free.
curl of
H.
M.
Okay.
Yes, okay. And I'll also give you J bound, which is
Divergence of B. Negative K.
not that right. And then I'll also give you this one here, which is
The negative divergence.
negative region. So these would be given. Okay. And what are you going to do? You're then going to show that what's the Ampere's law become? With these,
Yeah.
curl of H equals. Glad you're studying this weekend. J free plus
Mu F1.
partial
E.
of D with respect to T. Good. Excellent. Still ready for the point. That makes sense?
We are lost.
Okay. What does Gauss' law become? In terms of D and stuff?
The curl. No, the divergence of B.
Thank you. The versions of
D
D.
equal rho free.
Roughly. What do the other two equations become?
They say nothing.
They say the same. So they are.
The curl of B equal to 0. The divergence of
Okay, so
it should be
Sure that it was better.
equals to 0.
and
The curl of B
curl of
E
E.
equal partial of minus partial of B partial of C.
That'll be part B. Part C will be
Linear isotropic, which means that
you're gonna generalize for linear homogeneous isotropic dielectric. Then they become, for instance, this one becomes when you do that.
the divergence of E is rho free over epsilon.
So all the effects of the dielectric have been dumped into what?
That is dielectric constant.
That's one epsilon. Okay. What does this one become then?
The curl of B is equal to
UGF
UJ free
plus
mu
epsilon.
U epsilon.
What?
Or should we do something?
It's one else.
What else have I guaranteed? After this, only for the first three people.
Right. Wave equation
For
through
Linear.
for both E and B.
Mhm.
Okay. And you would do that by,
The vector identity.
which is
Oh no.
I give it to you. but still,
the curl
the curl of the
curl
curl of some V,
equals the gradient of the divergence
gradient of the divergence
minus the Flash.
minus the Fauci.
Yeah.
Those are the first two questions right there. Okay, equals zero. Okay.
Okay, theoretically, how much point are you taking if we say?
You said he's
I'm driving to Elson and tracking you down. It's not gonna be pretty.
That's junior.
Where's Junior? Junior who? I don't know who you're talking. It would just, coming to your dorm room, there would just be, that yellow tape that's.
I think the curl of it is zero.
Okay, so what are we doing? So we're doing now, we're writing our. Rate equation. We're saying that the first in the x direction was this MAX. And so what did we have here? We had this minus KX, and then we had our driving term. It was this M here like this. And then our driving term is this guy. Well, we took this last time. What's the next step of this?
Taking do you took the take the wolf.
Close.
Oh, we
Write it in terms of omega naught.
Okay.
So how do we write it in terms of omega naught? We divide everything through right now. So we divide everything through right now. This guy is omega naught squared. So I rewrite this as F naught over M, mid I omega T equals omega naught squared X plus this guy. And we classified this as a
linear.
linear,
Not homogeneous. Not homogeneous. Not
non-homogeneous,
constant curve.
second order. Okay. So what is our f of x term? We don't call it f of x, we call it f of t. This is our f of t term. So we look at all the derivatives of this and we get. What happens if I take the derivative?
It's just gonna be the same.
Nothing happens. Which is one of the reasons why we like that form. So what does it mean? That means that our non-homogeneous solution here, we don't do that. We call it
A exponential.
some amplitude here, A,
Exponential of I omega t.
and omega t. That makes sense. I want to actually go through in this. If you remember, we got something really quick. So, well, let's just go through and finish it up. So if I take two derivatives of this, two time derivatives, what does that give me?
I omega a e to the I omega t.
Two derivatives
E to the I or A omega squared.
minus. So I put on an I omega for each derivative. So this gives me minus omega squared a e to the I omega t. This gives me minus omega squared x. Right, because this whole thing here is this x. Or I should say x non-homogeneous.
Oh, you think you're taking the derivative of both? I didn't saw the dot, like it's okay. Just the notation is weird.
Okay. So now what do? We put this all back in here. And then what does that give us?
Zero.
So this gives us the omega naught squared. X non-homogeneous minus then this guy here. That gives us this here.
So close.
Okay, so that makes sense. Now, what did this show? We said that this right here is your amplitude. And what's unique about that amplitude?
It's independent of something.
What happens if I start changing the omega? Omega naught is fixed.
It like goes to infinity.
Yeah, this right here is a driving frequency. And what happens is, as this omega starts getting closer and closer to omega naught, the bottom becomes smaller, so this amplitude becomes gigantic. And what do we call that phenomenon? That's called resonance. Okay.
There need to be mass on there too.
Well,
Mass.
yeah, there should I'm here. I dropped it. So you should be done. Thank you.
Yep.
So if we plotted this guy, if we plotted our x, actually no, if we just plot the amplitude. Okay. Which is this F naught over m omega naught squared minus omega squared. Let's see, here's omega naught here. So what does that look like here? We said if this is 0, what happens? This is going to be some value F naught m omega naught squared. Now what's going to happen? As this starts approaching, right, this is versus omega here. As this starts approaching omega naught, what does this do? It's going to go like this, and it goes off to infinity, which is unphysical. That's what then what happens when we get on this side of it? Yeah, we're close to omega naught, but on this side of it, now it's minus infinity, so it's going to come like that. And as this value gets larger and larger and larger, it's going to go to here. Okay, that's going to actually, well, it's going to go to eventually it'll go to 0 here. So from on the negative side. Okay, that makes sense. But this part here, this is unphysical. Now, why was it really nice to use when we said the driving term is either I omega t? Because it could be a sine or a cosine. Why does this work out a lot better instead of using a sine or a cosine? So why is it useful to say that the driving term is this F naught, FD equals F naught e to the I omega t instead of this equals F naught, I'll say sine omega t. Does that mean it's the same idea? But why is it a whole lot easier to not do that?
You don't have to do sine and cosine.
No. If I assume this, so if we say the driving term is this, right? We have to look at derivatives of this. Which is what?
Minus sine.
Omega F naught
That's all.
cosine omega t. Do I have to keep on taking derivatives? No, I'm not going to get any unique piece. Right, this is unique. This is unique. That makes sense? So what happens here? I can now say that the non-homogeneous solution as well.
After that, sin omega t equals omega f by cosine.
Yeah, A sin omega t plus B cosine omega t. You don't need the F naughts or anything in there because everything gets dumped into that cos.
That's right, yeah.
Okay. Now what would you then have to do?
The geometry thing, and you put them all in one tray.
You could. How do you solve for anything?
You gotta take the like first derivative.
You have to take you have to put it back into the differential equation. So I'd be the first derivative of this. Am I still clear here? Am I worried? I am clear. So the first derivative would be what?
Omega cosine omega t
Omega A plus sin omega t
minus omega a sine omega
minus
t.
omega B sin omega t. Now I take a second derivative of this.
Which is omega squared sine omega t, a sine omega t minus omega squared.
Exactly. Now you have to sub this back into the differential equation. We do that. What do you end up with? You end up with the following. So our equation is this. Put this all in here. I get this F naught sine omega t. I take this to the other side. This term here is this one. Group like terms together. Now,
What is it called? Oh, you can factor out the. No, okay.
F not over n equals a.
the term in front of the sine omega t here, it's unique. So we just can say that A omega naught minus omega squared equals F naught over M. And what about the cosine?
So now we
What's the cosine over here? There is none. So then we would also get then 0 equals B omega naught squared minus omega squared. This one here gives me B equals 0. And this one here gives me the same thing we had before, this F naught and omega naught squared minus omega squared. Okay, but you can see it's a lot more work, not hard. Now, when you put in the friction term, it's going to be a lot more. Does that make sense? Okay. Now let's actually kind of put some pieces together here and let's see what we get. So let's just figure out how the index refraction would go with this. So with this expression, let's say so let's apply this. Apply to the index refraction. Less. Okay. So what do we have here? So here's our little nucleus. Here's your little spring. Here's your little electron. Here's your little incident wave. This E gonna be some E naught. E to the I. What did we call this direction? Do I have a direction? And you mind if I make it Z, then this will be Z, and this will be X. I think I changed it from what I had before, but that's okay. Let me call this the Z axis. Well, I'll call this AZ minus omega T. If I look at my little electron. Supply F of X is MA X to the electron. So what do I have? I have this minus KX. Then I'd have my Q E here. I'd say my drawing term. Okay, equals your M X double dot. And what is this going to be? This is going to be my, I'll divide through by the M. And I'm going to put in my term here. Now, I'm actually at a fixed value of Z. Right, this is Z here. This electron is fixed. So what's going to happen? This is really going to be basically, it's this guy here. This is a constant. Since Z is fixed. E to the minus I omega T. Okay. So if I put this in here. I'm just going to call this let Z equal 1. I'm sorry, let Z equal 0. Kill this piece here. So this is just going to become my E times my E naught E to the minus I omega T. Here I said where the FD is just Q times E. Direct stuff on top. Well, what's going to happen? You're going to get the exact same value we had before. Right? You're going to let X equals some amplitude E to the minus on omega T. Make sense? Got everything in we had before. Do you mind if I just jump to the answer? You okay with that? So this gives since X equals F equals here E naught mid minus time omega T over M omega naught squared minus omega squared. What is this right here?
Your FD.
That's my electric field. Makes sense? Now let's put all the pieces together. So what did we say N is? C over V, which is
1 over mu naught, or 1 over
the square root of the C is mu naught over epsilon naught. V is the same thing, but with V and mu and epsilon. So this is this. What do we do next?
mu over mu naught is essentially 1.
I simply said with this right here, for many things is about 1. Okay. Now there's a part of me that just wants to go and hide with Junior not being here. Just hide. Erase the board really fast. Just leave this stuff here. And that's. I inherited my father's bizarre sense of humor. Sorry. So then the sentence squared is what? Epsilon over epsilon naught. Epsilon is in lots. It's fine.
Don't worry about it.
It's fine.
There's the video.
Okay, so epsilon is
The program elevator.
I agree, which is epsilon naught
1 plus
1 plus
the electric susceptibility.
or epsilon naught. So our n squared is 1 plus chi. What do we say about our buddy chi?
It's Euclid's.
Sure.
You can also write that as a diagonal, no, 3 by 3 matrix.
Sure. First, we're going to linear homogeneous isotropic type.
Oh, the
Capital P, or your polarization vector, is this epsilon naught chi e.
yeah.
So this is 1 plus the polarization vector, epsilon naught times e. What's your polarization vector?
The sum
And then
of the dipole.
Sum of the dipoles, unit volume,
Yeah.
and that became what? It became the number of dipoles, I'll call that n sub d, times 1 dipole. So this is 1 dipole. Okay, which is what?
Q times.
Q times e, but the Q is going to become e, the meaning just a positive e. Okay. That times, I don't know, x. And then this is so divided by epsilon. But put that in there, and get this n squared equals 1 plus number of dipoles times e x over epsilon naught e. This guy pops into here. Okay, so for that gives me n squared equals 1 plus NDE e over e and omega naught squared minus omega squared here. This is over epsilon naught e. The e's go out, and what I'm left with n squared equals 1 plus e squared, the number of dipoles for unit volume, epsilon naught m, omega naught squared minus omega squared. Boom.
So is that another way to write over bracket in that? Yes.
Yes. So this is actually dispersion. Okay, so
So this first one.
so if I would plot this, if I plot n squared, this is omega, and here's omega naught. Okay. And let's say that let's say omega naught squared is large. Okay. What's going to happen here?
As your approach omega.
Let's say omega is 0.
Yeah.
This is large, so this term's going to be
There we
1 over omega naught squared.
0.
it's going to be pretty small. So what are we going to have here? Your n is going to be basically 1. Then what's going to happen? As you move closer to here, it's going to increase. It's going to go like that. And then what happens? When you get on this side here, you get this negative infinity. Now is it going to go to 0 anymore?
No.
It's going to go to, yeah, eventually this term here will go to 0, but then I'm going to set this 1 here. And it's going to come up here and it's going to asymptotically approach on that side here. So that's what this is saying. And this right here, this part right here, this is normal dispersion. Normal dispersion just means that basically that your n here your n squared increases with omega. Or n squared decreases with minus. How come? What is omega? 2 pi f.
Oh,
Okay, so if f is increasing, what is lambda doing? Decreasing. Okay, so it's basically you get the inverse relationship there. Okay, so that's just normal dispersion. Now we have to figure out how to deal with this unphysical part. Does that make sense? So how do we deal with the unphysical behavior at omega equals omega? I mentioned this a little bit on last, and I'm still clear. I am still clear. I mentioned this a little bit on last Wednesday. What do we do?
Is it friction?
You have to put in a friction term. So let's just go through and deal with it. The normal spring, then I'll figure out how to deal with it here. So basically what we do is we need to include friction. So when we do this, here's our spring. Here's our mass. If we're gonna put in something like that, it's all, it doesn't look like that. It has to be ejected. Here. This piece here, this is called a dash pop. Okay, I don't honestly know why. Okay, what does that represent? I've never seen one of these things. Well, actually, in some sense I have. Imagine you have a container here. Let's say you have honey in here. And then you have like a plunger here like that. So let's say you could hold this still. If you take the plunger and go like this, there's gonna be a lot of viscous force there on it. And it turns out that that frictional force here is gonna be proportional to the velocity. How do you make that inequality?
multiplied by a constant.
Well, put an multiplicative constant to say that this is gonna be some constant v times speed. Okay. What we have here is the following. When I do this, what does that give me?
The original term minus
It's minus kx
plus f naught.
minus bv equals m so
What about the driving turn?
I know it's in the bathroom. Just a minute. Okay. Now, what do? We divide everything through by m because we want to write this in terms of m naught in terms of omega naught. Here minus m. V is going to become dxdt. This is my f naught. Let's do it into the I omega t. M equals this right here. That makes sense? So what do? We rewrite this as this. Okay. Now what?
We can, oh, we already went in.
That we have to do.
So this is our non-homogeneous term, or f of t. Hey, but that's a really nice f of t, because what happens when you take derivatives of it?
Stays the same.
Nothing happens. So what form did we assume for the non-homogeneous piece? Some amplitude or some constant e to the I omega t. That makes sense? So what does that give me? One derivative of this gives me what?
The omega t a.
I omega a e to the I omega t.
Yeah.
Which is minus which is I omega x. Homogeneous. And a two derivatives of this giving me
Get it omega squared.
minus omega squared a e to the I omega t, which is minus omega squared x non-homogeneous. What should we do with this? Put it all in. Okay, this gives me f naught over m e to the I omega t equals. Anybody here? Anybody here? My buddy here. Why do we like this? What?
Be simplified.
Yeah, I just pull out my non-homogeneous term and I'm done. So this gives me omega naught squared minus omega squared plus I omega b for m x non-homogeneous. And how's that looking at here? That's still working. Make it a little smaller. Turns out this expression will also work in Vermont. New Hampshire. It's only true in New Hampshire. Work in Vermont too. There. Now, what happens at omega equals omega naught? Is there bottom zero anymore?
No.
No. No. Does come with a price. Why is there a price to be paid for this?
The I.
Yeah, we'll have to figure out what to do with the I. And what we're gonna have, how we're gonna have to treat this. Now, what we can say, solve the problem here. We can say when omega equals omega naught, the amplitude is large, but no longer infinite. So that's good. So let's tinker with this a little bit more. You never leave it like this. Why would you never leave the term like this?
You know. Imaginaries in the bottom.
You never want your imaginary in the bottom. Okay? Where do you want them?
The top.
In the top. So how do you get the imaginary in the top?
I remember. No. You multiply by the bottom, like by the bottom over the bottom.
Tinker with that.
Multiply by I over I.
No,
Multiply one in a fun fashion.
no.
True. Okay.
Yeah, it's true. You
So-
multiply you take the denominator over the denominator and you multiply it by the function.
If I have 3 plus 5.
Oh no, you take the conjugate of it.
Yeah, what do you have to do? You have to multiply both sides by the complex conjugate. How'd you get the complex conjugate of something? You just take the I term and replace it with
Negative.
the negative itself. This is 3 minus I5 minus I5. So what does this give me? 3 minus I5 over 3 times 3 is 9. I5 minus I5 is
I5. Negative I25.
Plus 25.
plus 25. Okay. What happens to the imaginary term?
It disappeared.
It goes away, right? Because this times this is minus I15. This times this is positive I15. So that's what happens when you multiply by the complex conjugate, you get rid of the imaginary piece. And so this is 3 minus I5 all over 34. Okay. There it is. So what do we get here? Yeah, it's accurate.
Yeah.
So we'll do this next time. We'll multiply by the complex conjugate of this. What's the bottom gonna go as? Omega squared minus omega squared
0.
squared. Okay. Plus the omega b over m squared. And then crap in the top. Okay. And then we're gonna have to figure out what happens is that our when we actually put this in a problem, we're gonna find out that now our index of refraction has 2 pieces. You're gonna find out that the index of refraction now is gonna have a real piece. Plus an imaginary. Okay. This imaginary piece is gonna give rise to basically it's gonna give rise to attenuation of the wave. But when we send the wave here, there's gonna be a certain amount of absorption, and it's gonna be related to this imaginary piece.
Isn't it like the same thing as the spectrometer?
Yeah, maybe it's connecting in with spectroscopy. Okay. Oh, yes.
If so, am I understanding this correctly? It's like, because that's the imaginary plane, it's like that waves being transferred to the absorption.
The absorption is gonna come from when you tinker with it. Okay, so we have a wave like this. Like that. It turns out what we're gonna be able to find with a lot of these things here, this K here, we're gonna be able to write like a unit part. This is a unit part. And so you get I here is going to minus sinus image and attenuated.
Okay.
I'm good.
This is gonna be given a slightly different. Okay, have you just.
Do you want me to give Ben homework to Ben, or do you?
Are you gonna see Ben?
Yep.
You can give